Okay.
Yeah, it's correct. Thank you.
Perfect. Thank you. Hello, everyone. Sorry. As Flavio said, sorry again, I'm Elisabetta Boella from E4 Computer Engineering, and I'm going to show some tests that we perform with OpenFOAM on machines available in our data center, which features different architectures. And before starting, I would like to thank many colleagues who contributed to the work that I'm going to show today. In particular, I would like to thank Filippo Marchetti and Daniele Gregori from E4 Computer Engineering, Giuseppe Giaquinta and Simone Bonà from Cineca, Flavio Galeazzo from HLRS, and Marta Gazzulla from BSc. So this is the plan for my talk today, and I'm going to start saying a few words about E4 Computer Engineering, and then I'm going to show the test that we perform with OpenFOAM on CPU platforms and then on GPU platforms, and I will leave with summary and perspective. E4 Computer Engineering is an Italian company founded in 2002 and based in the region Emilia-Romagna, which is called the Italian Data Valley. The company is a solution provider for high-performance computing, artificial intelligence, and cloud computing. At E4, we are very mindful with respect to new technologies which we propose to our partners and customers. And among our customers, we see international organizations such as CERN, the European Center for Medium Weather Forecast, Cineca, and Leonardo, just to mention some. Since 2013, we have been partners of several European projects, and we are partner of, indeed, we are partner of exaFOAM. exaFOAM is one of these projects. And we have different roles in these European projects. We are involved in the co-design and test, like in this case, test of application, like in this case, or we are involved in the development of prototypes, like in the case of the European Processor Initiative, EUPEX or Textarossa, or in the development of RISC-V platforms, like in the case of Tristan and Isolde. Here I'm just showing a couple of pictures from our tech factory. On the left, on the picture on the left, we see the integration room where novel clusters are assembled. In the center, we see what we call the burning room. This is very interesting because before a machine is installed in the premises of the customer, basically we put the machine on this rack with wheel, we bring it in this room, and then we do the initial boot and configuration based on the requirement of the customer, and we perform the so-called burning test. This is a test where for more than 78 hours we stress the component of the machine, the CPU and the GPU, and we do this to verify possible failures and to improve the reliability of the system that then we install at the customer premises. And to do this, we use like open source tools that my colleagues have optimized and modified to serve our purposes. On the right, instead, we can see our data center. In our data centers, we have 6 racks for 100 kilowatt. We have heterogeneous architecture. We also have beta versions of products that vendors gives us to test before they are released on the market. And the data center is used for both internal and European projects. And if you are partner of a European projects where we are also partner, then we can provide access to you to the data center. Okay, this concludes what I wanted to share with you about the company, and it comes to the more interesting part about OpenFOAM maybe. So as I said, we perform different tests of the code, and in particular, we selected 11 microbenchmark among the one proposed by the committee. And these microbenchmark use different solvers and uses mesh of different sizes. And we select these 11 because they are significant for industrial application, and they run on a reasonable time on 2 cores, which is the smallest number of core that we used in this test. So we run our micro benchmarks on several architectures. In all the architectures, we compile OpenFOAM with GCC 8.5.0 and OpenMPI 4.1.4. We use either OpenFOAM 2212 or 2306 in all the cases, but in 2 microbenchmark, the 6 and the 19, which needs a customized version of OpenFOAM. And we run this, we basically perform strong scaling test of this microbenchmark on this architecture listed here. We use one node Intel Cascade Lake, or one node, we did intranode tests. So we run this microbenchmark only on one node, and we use either one node of Cascade Lake or one AMD Milan, which are both based on x86 architecture, or Ampere Ultramax, and which is based on ARM Neoverse N1, or NVIDIA Grace Hopper, which is based on ARM Neoverse V2. Okay, so I'm going now to show you the result that we obtained. In particular, in these slides, we have 11 plots which show the time per temporal iteration in the code versus number of MPI tasks launched. Each plot corresponds to a different microbenchmark, and in each plot there are 3 curves corresponding to either the test performed on the result of the test performed on AMD Milan, or Intel in red, Intel Cascade Lake in green, or Ampere Ultramax ARM in blue. So just to mention, basically how did we compute this? We took the execution time of the microbenchmark. We neglected the first iteration because it's not significant, since there are also initialization operation there. And then we divided this time by the number of iteration minus 1. And each numerical experiment was repeated 5 times, and what we see here is an average over these 5 experiments. So what we can see from this plot? Well, the first things to notice is that, of course, the execution time increasing the number of MPI tasks. And this happen everywhere, but with few exceptions. For instance, in the case of the first microbenchmark, then we can see that when for larger number of MPI tasks on x86, basically the time does not decrease anymore but flatten. And then this happens also for a microbenchmark 2, 11, and 12, especially for AMD, where actually we notice sometimes some that increasing the number of MPI tasks, actually the time for iteration increase. And this happens also on ARM for microbenchmark 11. There are some cases where we observe some unexpected behavior, and in particular, in the case of AMD for the microbenchmark 4 here, and for ARM on microbenchmark 5 over here. The other thing to notice from this plot is that in most of the cases, basically, the fastest time to solution is achieved on AMD, and when less than 8 MPI tasks are used, actually the time per iteration AMD is half the time per iteration on the other platform. This is less evident for larger number of MPI tasks. The other thing interesting from this plot, according to me, is that Intel and Ampere Ultramax basically show comparable performance in terms of time per iteration. Using the data here, we basically computed sorry, maybe like this you see better. We computed the speed up, and as already mentioned, for some of the cases, also for some of the microbenchmark, as mentioned for the Grand Challenge industrial cases, also for the microbenchmark, we observe superlinear speed up, and we observe the superlinear speed up especially on AMD. So basically, using AMD allow for shorter time to solution, but also to get this superlinear speed up. And both this behavior are probably connected to the fact that these processors have larger L3 caches, where basically all the problem can fit. And so these allow to solve the problem faster, and also when using more MPI tasks, compensate basically for the overhead due to the communication. Using this data again, we then computing the efficiency in what are basically strong scaling tests. And good efficiency, meaning larger than 70%, is obtained when using only a number of MPI tasks less than 8 in this microbenchmark, as we can see from this plot. Here you have the efficiency on the y-axis versus the number of core, again for the 3 platform tested. The efficiency dropped dramatically in all the cases when using more than 8 MPI tasks. And this is due to the fact that OpenFOAM is a memory-bound application, and so when the memory bandwidth gets saturated, basically even if you launch more MPI tasks, you don't get much advantage because most of the time the processor is just waiting for data. In general, looking at this plot, it seems that x86 architecture show a better parallel efficiency than ARM, and on all the microbenches with fewer exceptions, with Intel actually performing a little bit better than AMD in this case. We also evaluate the FVOPS metrics for this in this test. The FVOPS stands for finite volume operation per second, which is a new metrics proposed to evaluate better the parallel performance of OpenFOAM. Basically, in this case, these metrics indicate the optimal number of MPI tasks to launch to achieve shorter time to solution, given provided a given microbenchmark with a fixed grid size and a particular computing architecture. What we can see from this plot, so again, here we have the FVOP matrix on the y-axis and versus the number of grid elements per core on the x-axis, and the 3 colors, the picture corresponds to different microbenchmark. The 3 colors correspond again to the 3 architecture: red AMD, green Intel, and blue ARM. And what we can see from this plot is that basically many of these curves have local maxima, which basically, as I said, means that there is where we are saving computational resources. So this should be the optimal number of grid of MPI tasks per grid elements per core to launch. It's interesting to notice that this local maximum depend on the architecture, besides on the microbenchmark, which was trivial. Also again, what this plot tells us is that AMDs where OpenFOAM perform better given shorter time to solution. We then compare two ARM platform, and in this case, we use a subset of the microbenchmark that we saw before. We use only 4 microbenchmark, and we compare the basically ARM Neoverse N1 with ARM Neoverse V2, so Ampere Ultramax in blue, versus Grace Hopper in purple. Grace Hopper is the NVIDIA super chip with also the GPU, but in this case we didn't use the GPU, we just used the CPU. I just mentioned this because Grace Hopper has 72 cores, while we could have used Grace. It was still not working at the time of this test. Grace has the double, so I just that is why I mentioned that I was say here that is Grace Hopper. So here on the first row, we have basically the time per iteration computed as I mentioned before, versus the number of core for the 4 microbenchmark and the 2 platform. And on the bottom instead we have the parallel efficiency. What we can see here is that on Grace Hopper, Grace Hopper CPU only, the time that the code, the time per iteration of the code is basically almost in all cases and for all the is always and for all the MPI task launched half the time employed by the code on Ampere Ultramax. But when we look at the parallel efficiency, Grace Hopper doesn't always perform better than Ampere Ultramax. Actually, in 2 cases, in MB2 and MB4, Ultramax has a better parallel efficiency at 32 cores than Grace Hopper. I just want to mention here that in both cases, we basically compile the code with GCC, so not with in both cases we compile the code with GCC and O3 flags, so it does optimization automatically, but we didn't put any flag for the architecture. So I expect to get better result once using maybe the NVIDIA on Grace Hopper, once using the NVIDIA suite of compilers with the proper architecture flag. Finally, I just want to show a test that we perform on GPU. In this case, we use basic OpenFOAM 2306 coupled with exaFOAM, which is the library written in CUDA. Simone spoke about this morning. And in this case, the test performed was Microbenchmark 1 lead-driven cavity flow 3D. And in this case, to compile the code, we use the NVIDIA suite of compilers 23.11 with CUDA 12.3 and OpenMPI for 1.44, which is the one shipped with the NVHPC. We performed this test with using mesh with different size, with 1 million cell, 8 million cell, and 27 million cell. And we are comparing here basically result achieved on using, well, these tests were always performed using 1 MPI task and 1 GPU only. And the blue line correspond to to test performed on Intel Ice Lake plus Ampere 100 at Cineca, basically using one node of Leonardo, then inside one node only one MPI task and one GPU. In red, instead, we use basically one core of the AMD Genoa coupled with Hopper 100. This is an architecture available in our data center at E4. And in green, we have result instead obtained on Grace Hopper at E4 using always one MPI task and one GPU. What we observe is that we get a speed up passing from A100 to H100 to Grace Hopper. And in all the three cases analyzed here, sorry, I didn't mention here on the y-axis we have basically again the time per iteration. In this case, we performed just one experiment, not 5, and again we compute this time neglecting the first iteration. So as I mentioned, like passing from Ampere 100 to Grace Hopper, we observe a progressive speed up. The speed up is increasing the number of points in the grid, in the grid. And yeah, the highest speed up was achieved indeed with the simulation using 27 million of cell on Grace Hopper. We got here a speed up of 2x with respect to Intel Ice Lake plus Ampere 100, and we believe that this is due to the highest memory bandwidth available on Grace Hopper with respect to the other architecture analyzed. I just finally want to mention that this number about 2 is basically what NVIDIA observed in similar tests performed by NVIDIA with the code GROMACS. Okay, finally, concluding, so OpenFOAM microbenchmarks appear to be more suitable for CPUs with larger L3 cache, like the AMD Milan. A larger L3 cache leads to superlinear speed up when performing strong scaling tests of OpenFOAM microbenchmarks. This is valid not only for the microbenchmark, but also as we heard this morning for the grand challenges and the industrial cases. From our test, we found out that the parallel performance is comparable for Intel, AMD, and ARM, with Intel showing slightly better numbers. We suggest users to evaluate the FOPS metric when deciding the number of MPI tasks for an optimal use of computational resources. And then finally, we observed that OpenFOAM coupled with exaFOAM showed up to 2x speed up when run on Grace Hopper 200 compared to x86 plus Ampere 100. And these results are similar to what obtained by NVIDIA with on similar architecture with GROMACS. Finally, for the next step, we would like to compare the performance on NVIDIA Grace Hopper and Grace between GNU and NVHPC, the NVIDIA suite of compilers, enabling also the architecture flag. And then we would like to perform tests of OpenFOAM on RISC-V, which is now available in our data center. And this concludes my presentation.
Thank you a lot, Elisabetta, for the very